सादर नमस्कार, सुप्रभात, अभिनंदन, स्वागतम, केम छो, जय श्री कृष्णा, वणकम, ए वेरी गुड मॉर्निंग। मैं अनिल भारद्वाज आप सभी का पीआरएल के 110वें अध्याय में स्वागत करता हूं, अभिनंदन करता हूं। आई अनिल भारद्वाज वेरी वार्मली वेलकम यू ऑल टू द 110th पीआरएल का अमृत व्याख्यान। We started this PRL Amrit Vyakhyaan as a part of celebration of PRL's 75 years of establishment, which coincided with the Azadi Ka Amrit Mahotsav. And it is meant to celebrate the history and legacy of PRL, which was established by Dr. Vikram Sarabhai in the year 1947. So it was also a tribute to Dr. Sarabhai, as well as to showcase the activities of PRL in the area of space science and physics. After completing the 75 consecutive episodes happening every Wednesday at 4 p.m., we started the PRL Ka Amrit Vyakhyaan 2.0 with a sankalp that every month we will have one PRL Ka Amrit Vyakhyaan. PRL Ka Amrit Vyakhyaan is delivered by very distinguished and renowned personalities or scientists in domains which is covering all walks of life, whether it is science and technology, engineering, business, law, management, arts, culture, sports, music, medicine, commerce, etc., etc. Today, that is 19th of November 2025, we have yet another very distinguished Vyakhyaan with us, Professor Raghunathan Srianand, who is the director of Indian Inter-University Center for Astronomy and Astrophysics, in short, IUCA in Pune. And he is going to deliver the Vyakhyaan on physics of young galaxies in early universe. As you all know, all the kids are always curious to look in the sky and to know what is happening, as well as to know how our own solar system got formed or how our own galaxy got formed. So this is a very pertinent subject where Professor Srianand is going to tell us more about how do we differentiate young and old galaxies and how actually solar system come into existence once galaxies get formed. I would like to thank Professor Srianand for agreeing to our invitation and to be with us today at the 110th PRL Committee. I would now request our colleague, Professor Pallam Raju, to kindly introduce today's speaker, Professor Srianand, to our colleagues on the WebEx panel, as well as those who have joined us live on the PRL's YouTube channel. Over to you, Professor Pallam Raju.
Thank you, Professor Bharadwaj. It's indeed a pleasant duty for me to introduce today's Vyakhyaan Karta of the 110th PRL Kamrit Vyakhyaan, Professor Raghunathan Srianand, who is the director of IUCA Pune. Professor Srianand is an Indian cosmologist and astrophysicist known for his redshift evolution and the cosmic microwave background radiation. He essentially uses spectra of distant objects to study various cosmological and astrophysical issues. And one of his most fundamental and very striking contributions to the cosmology has been the measurement of the cosmic microwave background temperature as a function of cosmic time, which is a basic prediction of the Big Bang model. And this work is now a part of the standard cosmology textbooks. Using detailed cosmological radiative transport, Professor Srianand and his student have provided solution to the so-called photon underproduction crisis. And using quasar spectroscopy, semi-analytical and hydrodynamical simulations and models, Professor Srianand and his collaborators have addressed a wide range of astrophysical issues related to mapping the time evolution of cold gas, physics of intergalactic medium, galaxy and structure, various feedback processes, and the missing baryon problems. He has received several awards and honors. Notable among them is that he is the recipient of the Shanti Swarup Bhatnagar Prize in the field of physics. and he's a member of the International Astronomical Union, IAU. He's a fellow of Indian Academy of Sciences and the Indian National Science Academy, among many other achievements and accolades. It's indeed a pleasure that he's here with us today to deliver the talk, which he has. It's a very, very pertinent and exciting topic called, and that's titled Physics of the Young Galaxies in the Early Universe. With these few words of introduction, I'll request Professor Srianand to please take it forward. Professor Srianand.
Thank you very much. Good morning to all of you, and it is indeed a privilege to come and share the kind of things we are doing at present. Let me first share my screen and start my talk. Please confirm you can see my shared screen. Is that?
Yes, we can.
Okay.
Yes, we can.
Okay.
Thank you.
So today, the topic of my talk is to tell you about various challenges we face in forming galaxies in very early universe. Why this is interesting today is that now for the past couple of years, we have a space telescope operating from one of the Lagrangian points called JWST. And since it is a very big telescope, it is able to see very distant universe. And whatever it is seeing is basically our universe at a very young age. Okay. So that is producing some challenging results. So in this talk, what I will do is that first few minutes, I will explain what what we mean by galaxies and what kind of physics we need to do, we need to incorporate to understand a galaxy. Then I will introduce what is JWST seeing and what are the challenges in these observations. And then probably in the later 1/3 of my talk, I will just see what are the efforts we are making in IUCA to address this issue. Okay, in any stage, if my slide is not moving or I am not audible, please warn me. Okay, I am unable to see the participants now.
Yes.
First thing is that this slide I just show a typical galaxy when it is seen at multi-wavelength, right? If you go from left to right, you are seeing the same galaxy imaged in radio, infrared, optical, ultraviolet, and X-rays. Clearly, the morphology of this galaxy is looking very different depending upon what wavelength you are looking at. So we also know from basic physics, the radiation coming at different wavelength means there are different physical mechanism that is generating the radiation. For example, when we are talking about radio, we are looking at high relativistic electrons moving around the magnetic field. So if you look at a radio image, basically you are imaging the distribution of relativistic electrons and magnetic field in a galaxy. As you move towards optical, typically optical light is coming from stars like what we have sun and nearby stars. So basically you are looking at black body emission coming from stars, but not exactly the radiation, but it's modified by whatever material which is present between the star and us. But when you move on to X-rays, you are basically studying high energy charge particle being accelerated by various mechanism. One could be Bremsstrahlung, where you have protons accelerating an electron. So when you look at a X-ray image, you are looking at a charge particle being accelerated by electrostatic forces. So clearly, when you look at a galaxy, if somebody is asking you to form a galaxy, you are thinking of forming a galaxy where with different components contributing to different energy radiation at different wavelengths. So that means clearly when somebody asks you to form a galaxy, you should worry about forming stars. Not only stars, you should worry about this forming these magnetic fields, charge particle in the magnetic field, and also look at very high energy charge particles which are emitting X-rays. So this is just a kind of simple thing I wanted to introduce. So this is already a big challenge to have all a galaxy appear exactly like the way it appears in observations in your models is a big challenge. Second thing is that it's also interesting to see. This is a very interesting illustration. So the same region of the sky imaged in the starlight is shown in the left hand side, and the same thing imaged with radio telescope in 21 centimeter hyperfine transition. This is basically you are looking at hydrogen emission from the galaxy using radio telescope, like for example our GMRT. So if you look at the left hand side image, you can identify three kinds of isolated galaxies, and it look like they are kind of they're quiet and there's nothing spectacular happening there. But when you look at the right hand side image, this is in H1, you can see that all three galaxies are also seen in hydrogen. That means all galaxies have sufficient amount of gas. But not only that, you look at them being interacting with each other. So that is the main thing, right? Even though we are thinking of galaxies as an individual entity, how it is evolving may be governed by the way they interact with the surrounding medium, which can be easily picked if you look at the distribution of gas around individual galaxies. Okay, so I'm just introducing the second component. One is that we need to worry about stars, plasma, and gas. And because a galaxy contains all these components, how it is interacting with its surrounding is also going to affect the distribution of these components, which we have to be conscious of. Next thing is that in the same set of galaxies, it is the same three galaxies. We are looking at the topmost galaxy in the right hand side. If you look at the topmost galaxy and image it in the H alpha band, a narrowband image, you can just see two colors, right? One is in white color, and another thing is a conical kind of thing you can see in red color. Basically, what it is that we realize that several galaxies have huge velocity, high velocity outflows, which throw large amount of material from the galaxy to the outer space. Okay, so this is one of the depictions. So you can clearly see this picture of M81, 82, 83 has a lot of story to tell us. One is that the galaxies, even though they appear isolated in optical, they may be interacting very intensely. The second thing is that individual galaxies can also have kind of flows which is linking whatever happened in the galaxy with the surrounding medium. So that means one should also worry about the gas dynamics in a galaxy through interaction as well as whatever effort which goes on inside the galaxy itself. The next thing which we understood, which is very well known, means I'm just for the completeness I'm giving you. Here is a galaxy which is a spiral galaxy. If you look at the gas component in the galaxy and use spectroscopy to find how the galaxy is rotating, the gas is rotating around the galaxy as a function of distance from the center. This is what is plotted in the black plot. X-axis is the distance from the center, y-axis is the average velocity one sees along the major axis. The red curve, what you see is what one observed. Basically, what happened when you move away from the center, the velocity keeps on increasing. Afterwards, it reaches a steady constant value. This velocity, we believe, is because the gas is under the gravitational potential, and as you go out, the potential is changing, and velocity will be proportional to the potential, right? That's what we are getting. A derivative of the potential will give you the velocity. So clearly, what you expect is that if all mass in our galaxy is concentrated in stars, you expect a curve like what you have in blue dashed curves. This is mainly you are using Newton's law of gravity, and you see that at any radius, the mass which is important is the mass within that radius, right? So if you do this, as you go away from a galaxy, at some stage the stars, the distribution of stars will stop. So beyond which the galaxy will appear like a point source. So the velocity should fall as like Keplerian way. But in reality, in none of the galaxies, even if you go outside the distribution of stars, you find gas moves at velocities which are much larger than what you expect from a simple Keplerian problem. So this leads us to believe that all galaxies have dark matter, and now what we understand is that dark matter is the predominant component of gravity in our universe. So till now I just introduced you. Basically, if you look at a galaxy, we used to think that it is a collection of stars, but we also realize that in addition to stars, you have lot of amount of gas which is present. Gas can be in different phases: cold, hot, and warm, and highly ionized plasma. And this gas component, how it behaves, will depend upon the dark matter which is present in the galaxy interacting with the surrounding galaxy and whatever activity which goes in the galaxy. So this is basically building up towards what you want in a component. Okay. Lastly, another interesting point we know about every galaxy, almost all galaxies host a supermassive black hole in the center. That is revealed by strong concentrated emission in the form of active galactic nuclei, whose energy density, or if you say what is the luminosity energy per unit time, from such a very small region like our planetary system, is of the order of whatever energy released by the whole galaxy itself per unit time. So this has been understood as a very supermassive black hole, which is staying in the center of our galaxy. So this is well recognized now. So if you are forming a galaxy, you should also think about forming a black hole in the center. So clearly you see the scales. When you are looking at a scale of interaction, we are talking about 10 to the power 24 centimeters or 25 centimeters. If you are thinking of a galaxy, you are talking about 10 to the 22 centimeter. That's the scale we are interested in. When you are talking about a black hole, you are talking about 10 to the 13 to 10 to the 14 centimeters. Okay. But what makes the problem more interesting is that it is also found out that x-axis what is plotted is a proxy for mass of the galaxy. Y-axis what is plotted is the mass of a black hole in the center of the galaxy. And as you can see that there is a strong correlation over several orders of magnitude in mass between mass of the galaxy and mass of black hole. What it tells you is that galaxy knows what kind of black hole it has to host, or other way around, black hole knows how far it can grow in a galactic environment. So this is a very interesting problem, because we know that black hole influence is of the order of 10 to the power 13 to 14 centimeters, whereas the galaxy scale, as I mentioned, it can be anywhere between 10 to the 22 to 10 to the 23. So clearly, there is some physics which transfer a kind of information from the smallest scale to the largest scale. So these are the kind of challenges you have to, suppose if you ask me to form a galaxy, I have to form all these things. I have to have a dark matter component. I have to have stars formed in the dark matter environment where gravitational potential is completely dominated by dark matter. And in addition to this, I should have huge amount of gas which is moving in a particular way. And the gas can have different patterns, like it can be cold, it can be ionized, it can be moving, charged particle moving in magnetic field, or plasma where you have Bremsstrahlung emission happening. So this is the kind of a challenge one has when people say we are forming galaxy, means you have to form all these relationships, and whatever thing we have noticed, it should be reproduced in the models. Okay, so basic idea behind forming a galaxy now, what is understood is that one believes the main ingredient, the way we understand now, is that main ingredient is that we have some kind of uniform distribution of matter in the universe. Some gravitational perturbation leads to small regions being gravitationally collapsing, right? That's the region. This region, whenever this region start collapsing, we call it as a galaxy, which means in this region we are going to form various things. So we are going to, the basic ingredient is shown in the right hand side. So you have a dark matter region which is beginning to collapse into itself. So material around that region, so-called what you call as intergalactic material, is being dragged into this gravitational potential. And when the matter fall into the potential, it will get heated to higher temperature. Then it cools, and then it collapses into smaller region to form stars. So this is, you just follow the arrows in the right hand side. So you material falling into the dark matter potential cools and collapse, and then it leads to star formation. Star formation means basically you are running a nuclear reactor. So by the time the nuclear fuel in the center region dies, it becomes a supernova and throws all the material into the surrounding medium. And this newly cooked material, which is basically yield from the nucleosynthesis, is now mixing with the what we call surrounding gas, which is already present, and it enriches the gas with this newly created material. Again, this mixed gas can go through cooling, collapse, and form stars. So this is a cycle which has been shown with arrows, because that you can clearly see in the middle of the plot. So this is the process which goes on. That means when you start a galaxy, you will start with hydrogen and helium. But as time progresses, it will keep adding heavier and heavier elements. And each time it adds a heavier element, you know that some set of stars have just died. That means like it has gone into supernova or something like that. During this process, little bit amount of gas can also leave the galaxy and go away, like the way we saw in one of the images. Okay, so this kind of a simplistic picture one has to explain how galaxies can be produced and formed. Okay, this is kind of a simple model which has been accepted in the community now, and this is what one is going to prescribe to it. But just wanted to give you some ideas. For example, so this is all okay, but we should worry about what kind of time scale one is going to talk about. Okay, so if you are thinking of a star, what is the shortest time scale over which a star can live, and then it can create nucleosynthesis and then die? It can be of the order of million years, right? So typically about 100 million years is what a typical star of 10 times the mass of sun can live. So you can just remember 100 million year. It is not a big number if you are comparing with 10 billion year for our age of the universe. So it is never a problem when you are thinking of forming a galaxy today. Okay, so this is the point I wanted to mention. But there are complications. Now we understood that this is what is the process we will be involved with. So just I'll give you the timeline. So whatever I explained over word is also shown here. So it is believed that there was a Big Bang, and then universe was extremely hot, and various elements were created, and it is going through the process. At some stage, you have created light elements like hydrogen, helium, lithium, beryllium, and all. And the radiation was closely interacting with this material, and as universe keep on expanding, at some stage, the radiation decoupled from the material, and the material becomes stable element. So these are the things we know. And in this time, when the whatever radiation decoupling from the matter, we call it as recombination epoch. At this epoch, it is found that there are small, tiny fluctuation in the density field of the universe. Universe was uniform at a level of 1.1 part in 10 to the power 5, but there are tiny fluctuations which are there at the order of one in 1/10 of a billion, right? Million. So these fluctuation, one believe, are the seeds for creating whatever galaxies we have today. So typically what happens is that these small fluctuations grow and they form first set of galaxies, and galaxies evolve, and present day we find these very massive and excellent galaxies which you can see. So I have also added a vertical line, whatever you see in yellow. This is the distance up to which the JWST can detect galaxies today. Okay, if you take what is the time scale of, if you believe in the Big Bang model, what is the age of the universe at that time when the JWST is actually performing detecting the galaxy, is at present it has reached a time scale of up to 400 million years. It's just see 400 million years. 400 million year is very close to the lifetime of few times the lifetime of a typical star. So this is where we are now moving towards problems in forming galaxies. So I explained to you what all the things you need to form galaxy. I also told you typical time scale of formation of a star is of the order of 100 million years. If I just ask another question, we can ask is that we are living in Milky Way, right? So you go to the edge of the Milky Way and you say that I just throw a particle to take a test particle and let it go and free fall into the central. How much time it will take to free fall to the central region? Again, it will take about 10 to the power 8 years. If you just take the typical velocity in the gravitational potential, how much time it will take to travel through that distance of something like 10 to the 3 times 10 to the 22 centimeters, you will figure out that these numbers are about 100 million years. Clearly, if you follow conventional way of forming galaxies, you should not be seeing too many galaxies at this time, because this time scale allowed by the Big Bang model is too short at this time. So this is the main problem I'm going to pose today. The idea is to see JWST is observing something, and the observations are so deep that you are going to the almost edge of the universe, and you are not supposed to see certain things which you are seeing, and how are you going to manage that? So this is the problem we are going to address today. I hope up to this point you are following me the problem. So what are the kind of instrument JWST has? JWST basically operate between 0.6 to 5 micrometers. So basically it covers optical, NIR to mid infrared regions. It also has imaging capabilities, which is a spectacular thing because it's in the space. So there is this is almost like diffraction limited kind of images. So you will get sub-arcsecond scale. For example, one is probing at a few hundred parsecs at these distances, right? This is remarkable. It's a 6-meter telescope in space. So which is this kind of telescope we don't have in India, even in ground. So that tells you kind of powerful, how powerful this telescope can be. It can also have a spectrograph which can operate at different resolutions, the resolving powers, and either you can produce a high resolution of a particular object, or you can produce little spectra of several objects. So they have various varied things one can do. Of course, it is since it is covering wide and interesting range of wavelengths, it can do a lot of interesting science cases, starting from looking at planets to dust grains in nearby galaxies to the very distant galaxy star formation in very distant galaxies. So I am going to focus mainly on light from first stars and galaxies. These are done through images and spectroscopy. Okay, this is the main thing. Doing spectroscopy of a very distant object is possible now thanks to this spectacular instrument. Before going there, I will introduce something. So in astrophysics, we measure the distance and age through what is known as redshifts. Redshifts are nothing but, if you look at wavelengths of different objects, different spectral lines, and they don't come at the wavelength of the rest frame in the laboratory wavelengths. They come at slightly larger wavelengths, and this is understood as the effect of expanding universe. So typically, if the shift in the wavelength is by order few, suppose you say that the wavelength is shifted by factor 11, then the way we understand is that we are receiving a photon from an object which is at okay. Where if you find the shift in wavelength is by factor 11, what we have to understand is that we are detecting a photon from a universe. When it was emerging, the universe was 10 times smaller than what it is today. So basically, this photon was emitted from an early universe when the universe was smaller by factor 10. So similarly, if you think of a redshift 3, that means the wavelength is shifted by factor 3, you can think of this object was present, and when the photon started from that object, the universe was 2 times smaller than present day values. The light has taken so much time to travel from that object to us. Okay, that's what it is. So typically, the spectroscopic capabilities of JWST allow us to detect galaxies between redshift 7 and 13. These are the range of redshifts which we can measure, which we have measured spectroscopically. This is what I have pointed out with the horizontal lines. If you just take a typical universe, which we believe is the universe in which we are living, the connection between the age of the universe and the shift in wavelength is given by this red curve. Okay, so now if you take that the shift is by 13.2, then the age you are talking about is something like 300 million years. If the shift is by factor 8, that is redshift 7, then you are talking about something like 780 million years or something like that. So it's clearly this poses the problem that JWST is observing an young universe. This is why my title of the talk is kind of young galaxies in a young universe. So this is what we are up to. So now let me just give you few glimpses of what are the things it is. This is the deepest image taken with JWST, and you can see that each one of these dots, white color dots you see, is the distant galaxy. So it's very deep, and it can, and also these bigger galaxies you see, there are so many spectacular details in which one can study the morphology of the galaxies. The next thing I'm showing is that in this image, we have identified about 4 such small regions, and for these regions, spectra are taken, and you can see there are boxes in the middle of the panel with the different numbers written, right? Z equal to 13.2, 12.63, 11.58, 10.38, etc. These are the objects detected with wavelengths being shifted by this amount. The spectra are shown in the rightmost corner, and the vertical red line gives the indication of where the Lyman alpha transition from these galaxies should be present. And you can clearly see the highest redshift measured spectroscopically is 13.2. That means we are going to, you are detecting an object from the universe which was 12 times smaller than what it is today. Okay. Or other way around, if you remember my previous slide, it is something like 300 million year old universe. Here is an object which was found at that time scale. Okay, so this is the first thing I wanted to tell you, that the people are now measuring galaxies with good accuracy because it's spectroscopic. It's not like this thing. The second thing I wanted to show is that again is yet another galaxy, and we focus mainly on the rightmost side, where there is a spectra shown, and you can see different emission lines are marked. Okay, so just focus on that lambda. You see this vertical lines with Mg2, O2, neon, helium, and all. So this is the thing which is interesting, because these are high resolution spectra where you can see this lot of emission lines are there. The point to emphasize are, this is around redshift 8.7. Again, you are talking about something like 500, 600 million year old galaxy, old universe. You already see emission lines. That means stars, sufficient amount of stars are formed, and stars are exciting the region around them. And where this gas, when it is excited, they emit these emission lines. That is the first point to look at. What is more interesting is that we are not seeing only hydrogen and helium. You are already seeing oxygen, neon, magnesium, carbon. So it's clear Big Bang doesn't produce this kind of heavier elements. At least we don't know how to produce this heavier elements starting from Big Bang. Usually we produce all these heavier elements by forming stars and cooking the material in the central region and throwing them out through supernova. The fact that we have sufficient amount of oxygen, neon, helium, and all, magnesium are detected, means that we are looking at a region which has already gone through several cycles of star formation. Just remember, a typical OB stars or massive stars, they live shortest, and if you think of how long they will live, it is of the order of 100 million years, or in a very extreme cases, 50, 60 million years. And we can clearly see that to produce this much amount of material, chemical elements, you need to have several cycles, at least 2-3 cycles of star formation has to happen. So it's clearly you are living in a universe of 600 million year old, and you are talking about some process which should have gone through for a few hundred million year time scale. So this means, first of all, you are detecting bright galaxies at large distances, early universe. Second thing is that they are not looking like a pristine region, right? They are already looking like a region which has gone through several cycles of star formation. Okay, so this is the kind of information one gets. I just wanted to show that you can also get information about each galaxy by looking at various wavelengths. So here it is shown starting from 0.6 micron to 5 micron region where the images are taken. Okay. So next comes the interesting problem. So what happens is that if you detect one galaxy, okay, you can say that it is a statistical fluke. Okay, if you take Poisson statistics, one is like almost like 1 plus or minus 1. So you can say that, okay, for some reason you are looking at a region which is very special. So you don't worry about this, because it can be done. So people quantify number of such galaxies per unit volume. This is known as luminosity function. Luminosity function is nothing but you just consider a unit volume. See, one megaparsec cube. Megaparsec is 10 to the power 24 centimeters. So if you just you put a box of that size and count how many galaxies are there within that box. This is what is plotted here. For at different redshifts, means different distances, right? 9.7 and 12.7 are the two values. You can concentrate on the topmost left panel, where MUV you can think of like an indicator of brightness, and phi is the number density per unit volume having that brightness. Okay, so these red dots and blue dots and all are numbers which are measured. So what this thing tells you, what luminosity function tells you, is that in an average sense, how many galaxies you have to form per unit volume. So this puts a lot of tension on your simulation itself. If you find one galaxy, you can say it's a rarity. But if you are finding large number of galaxies, it is going to be a problem. This is what is what is happening now, because we are finding too many galaxies, not only one. And this is depicted by picture here. What is plotted here in the x-axis is the redshift. Redshift, again, you can think of like size of the universe compared to present day size, right? 116 means 15 times smaller, like that you can think of. Y-axis is that basically your number density of galaxy per unit volume in some sense. Okay, it's written as a rate, but you can imagine this is same, right? The curves which are drawn are the curves which we thought is the way universe will evolve before JWST is there. So whatever yellow curves you are seeing, you can clearly see that it is a sharply falling curve. That means as you go back in time, you are expecting less and less number of galaxies. This picture is up to 2018, right? At that time, we thought that there are not many galaxies around redshift 12, 13, 14. These green, red, and blue points you are seeing are the new measurements, and they are clearly challenging our original thing that you need to produce more galaxies at higher redshift compared to what we thought before JWST is launched. I think this is the problem which has been posed here. And people who are working on this field are beginning to feel that, oh, it is going to be difficult to do the same. Okay, that's the I'm just setting up the problem which we are going to address. I think I've also given you a few indications. Okay, let's focus on the left and bottommost plot. Here we are actually finding the size of the galaxy. Since you are having images, you can also find what is the typical size of the galaxy at different redshift, again, different time scales. Okay, and we can clearly see that in the past, the galaxies were extremely small and compact. Okay, so this is an interesting problem because we can measure the sizes. These galaxies are roughly 10 times smaller than the present day galaxies. If you are thinking of what is the size of present day galaxies, how they are compared, but they have the same amount of luminosity. That means they are producing same amount of light per unit time, but the sizes are substantially smaller. That means the density of stars in these galaxies are going to be much higher. So this is the another problem one has to bring in. You are forming too many galaxies too early in time. They are also producing chemical elements, but they have to be formed at a much denser environment. Is it naturally explained in such a situation? This is the kind of problem is being posed. The initial results of this issue is that we have all the simulation people do. You normalize, or you simulations have several parameters, and people fix the parameters by looking at what we see today. Clearly, if you take those parameters and extrapolate to what we should have seen in the past, and people are finding that we should not have produced this many galaxies theoretically also, that has led to the issue that is there a problem in the cosmology in which we thought like we put all our bets on. Okay, so that's the problem I want. So I'm just giving few more examples of spectra. This I have already explained to you, so I will not spend much more time on that other than saying spectra are revealing large chemical enrichment even at very early redshifts. Okay, as early as the universe was 10 times smaller than today. Okay, that's the key point I want to carry. And lastly, while doing all these things, I also mentioned about one of the key ingredients of galaxy is the central region where you have a black hole. Okay, do we detect black holes from JWST observations? It seems that one is detecting them, and these are now actually we are detecting a new population of black holes known as little red dots. So what are these little red dots? Basically, they look like a red colored dots as seen in the top left panel of this slide, and you see the red colored dot. If you go and take the spectrum looks like a V-shaped color. So you can just see spectrum in the top right panel. I have put two straight lines. One is in cyan, another is in orange. Orange shows that as the wavelength increases, the flux is decreasing, whereas the green shows that when the wavelength increases, the flux is increasing. Okay, so it looks like in these objects, when you go from whatever 6,000 angstrom observed wavelength, as you keep increasing, the flux falls. It's like a blue color. It appears like blue color in the low wavelength, and it becomes red color in the high wavelength. And this is a very unique object which has been now, which is a puzzle which people are still looking at. So this goes by the name little red dots, and producing such a spectral signature is not very easy from theoretical pictures. The another indication which is coming is that if you look at the width of the emission lines, they are substantially broad. Their widths are of the order of few thousand kilometers per second. These kind of widths are usually associated with black holes, right? This is how we detect black holes. So broad emission lines are the indication of presence of black hole. So now one of the conjecture for little red dots is that these are young black holes, which are actually being formed at early stages, surrounded by large amount of dust and metals. And this, while these guys are still in infancy, they are going to shred this element and become a big bright quasar at some stage. So this is the picture one is depicting, and we can say, okay, it is natural, right? You are expecting that all galaxies should have a black hole. Why not these galaxies showing black hole? And this kind of V-shaped spectrum is also understood that outer regions have a star formation, which is what you see in the blue part, and the red region is dominated by quasars, which is what is red and quasar light. So again, this is the conjecture, which has not yet been confirmed, because these are all very new observations. So the whole thing is lasting over less than 2 year old. Okay, so that's why it's interesting for us. So shall we go and look at, is there any problem with them? Why can't you form black holes? The problem is what is shown in the right hand side. Okay, so you go to the right hand side figure. What is plotted here is that, again, it is a luminosity function. You remember what is luminosity function? Luminosity function is nothing but number of galaxies per unit volume, something that is what is shown in that blue color curve, and what is shown in the red and the green are the number per unit volume seen by these little red dots. Okay, so this is what it is. Suppose if you take whatever we know about our quasars and black holes before the JWST observations, what is the prediction that is given in the red? The red color thing with the dotted thing is what you expect. So basically what we are finding is that we are nearly finding 10 to 100 times more black holes, right, at higher redshift compared to what you would have predicted based on whatever we have studied over the last billion years. So again, for some reason, the universe was in a hurry to produce all these stars, black holes, and other things. Okay, this is the kind of settings. I think I have given you very good overview of whatever we are seeing in JWST, why it is challenging the cosmology itself. So this is highly nonlinear problem, and one has to address it through detailed computational calculation. So we started investing our time and effort in building numerical simulations. So the rest of the time, I will just go through our attempt to form galaxies and other things, and I will explain what kind of thing we are getting into, at least to give some idea of what kind of milestone we could achieve with our simulation and what is the understanding we have about these galaxies. Okay, to start with, we call this a ninja simulation. It is a collaboration between NICER and IUCAA, and we are building a large-scale hydrodynamical simulations where we incorporate all physics related to formation of stars, gas, whatever component I described in the beginning. All of them are consistently being followed, and the core of the computation is from publicly available code, whereas we have implemented a lot of specific physics to make sure that we will be able to vary our parameter and address the problems which I have indicated to you in the beginning. So these are people involved in our simulation team. So just to make a comparison, people involved in astrophysics will know the benchmark simulations are what is known as illustrious TNG. These are the simulation run in US with typical box sizes. So our universe in the simulation has a size of something like 300 megaparsec. Megaparsec is, as I mentioned to you, 3 times 10 to the 24 centimeter. It's a very small patch of sky, and the parameters which they use are something like they have 2000 cube particles. This is the dark matter particles and gas particles, and subsequently you will start forming stars and other things. So our simulation matches with this TNG simulation. That's what I wanted to highlight. Our simulation, whatever we are doing, is benchmark with the benchmark simulations which people use worldwide. So why do we need to run these simulations? Again, if it is already available, first of all, we want to demonstrate that it can be done in the country. That's the first thing. We have capability to run it. Second thing is that these simulations, as I mentioned to you, they were calibrated to produce the local universe. So they miserably fail when you go and start observing at the higher redshift universe like observed by JWST. That's why we thought like we will focus on JWST and produce simulations which will match that. Then see how you can self-consistently explain whatever we are seeing today without without violating any physical conditions. Okay, that's the main motivation. So at present we try to address. So I'll just give you a glimpse of our simulation now. I hope I'll be able to run. Okay, you can see that this is the simulation starting from initial conditions of random universe, and you can see structures are being formed. This is the gas particles, and wherever you find a strong concentrated light, these are the regions where we form galaxies, and there are regions which are dark in space. These are called voids, and these void regions are devoid of elements. And the same region in the right hand side, what you are seeing is the what you will see if you generate light from these galaxies. So these are the simulations where we can convert all our simulated quantities in the observables. I'll give you some examples. So here you take one of the galaxy, the red patch you see is hot gas, the blue patch you see in the top is the cold gas, and the bottom you can see star distribution. For these are two different galaxies in our simulation. Just wanted to illustrate the kind of resolution we can achieve in our simulation. The idea is that once we are done with our earlier result, all these data products will be available for public to play, for any researcher to play with for their own research. Okay. Again, simple one small snapshot of our galaxy and blow up image, and you can see what kind of details in which you can look at the galaxies at very early epochs. So we are basically simulating galaxies in the same redshift range as the range covered by the JWST. Okay, so let me just go through some of the results and then we'll see. So you can just see these are the light. These are like, we now make the images of our simulation exactly like the way it is done by JWST with different filters and all. And you can see even at very early universe, we are able to produce the spiral arms and things like that. Okay, so nothing has changed as far as physics is concerned. We have fine-tuned our parameters, but these parameters are well within the realm of what is understood by the physics itself, right? Because we are not going to an extreme parameter like the way one has to do if you are doing semi-analytical model, because there are a lot of hidden nonlinear physics. If you don't capture them properly, you end up having some parameter values which are unphysical in your models itself. So this is the thing. The first thing I wanted to show is how we compare with other simulations in the universe. So in available in the literature. So these are the kind of what we have done here is that we are looking at mass of different galaxies. How many galaxies per unit volume are present with different masses? The black color curve is our simulation, and there are other simulations which are recently become public, and we are just comparing our simulations with their simulation. And as you can clearly see, when we are at low redshift, all simulations match very well, because these were the all parameters of the simulations were fine-tuned before JWST come online. Ever since JWST come online, we are beginning to see that we have wide variety of possibilities at higher redshift. One has to tune your parameters to match them. It's not sufficient to have whatever we have done in the past. So that's the, I just wanted to show that these simulations are not very random, and we are self-consistent, and we are producing the result. At least first attempt is to produce existing results, which we achieved. So now I just give you an example of how it looks like for each point in our simulation. We can generate a spectrum as if we are observing them. We can also make images. This is what is demonstrated here. And we take care of emission coming from gas. We take care of emission coming from hot gas. And we transport the radiation through the gas which is present, the scattering. We take care of dust, formation of dust, and we also take care of the scattering by dust, etc. So if somebody is interested, I can explain during the during our this thing. So first thing I wanted to focus on is the left hand side. This is the thing I talked about. I said like one is finding large number of galaxies, and this is quantified by what is known as luminosity function. Are we producing these galaxies in our simulation? So the dotted line in the left panel, all the points are observed data points from JWST. The dotted curve is the raw light we produce in our simulation. But if you do the proper transport of this radiation from that galaxy to us, what we get is the black color curve. And you will now agree with me that we have no problem in reproducing whatever we observe as a galaxy luminosity function. Other way of saying is that the models we build have no issues in reproducing the galaxies at higher redshift. So now you will ask what are the, I will explain what are the things we have to change to make sure that our observations match with the JWST observation. So this is the first result. First result, I am saying that the number of galaxies which we produce in our simulations are in right ballpark compared to what we have from JWST observations. So I think not only this there are three plots. This is our simulation versus observation comparison up to redshift of 10. That means till our universe was 10 times smaller, it seems that we have a model where we can self-consistent. Say we fix the parameter once and it explains the redshift evolution in a self-consistent way. So it looks like to the first order, we have no problem in explaining the universe, which is up to 1/10 of the present day universe, with a simulation which is self-consistently run. Okay, so this is the first result we wanted to highlight. Second thing I want to do is that, are you producing, is it true for all redshifts? No, it's this is the problem we are facing now. When we go to the universe, which is 13 times smaller or 12 times smaller, we are finding that our simulations are producing slightly less number of galaxies compared to the compared to what has been observed by JWST. Okay, so this is the present status. Then we have figured out what is the reason behind, and we are addressing it. There are two possible reasons, which I will again explain in my last slide. So basically, we started with a simulation. We are able to go up to 1/10 of the universe. We are okay, but if you go further than that, we are beginning to face some issues where there are more galaxies observed, at least a factor 2 more compared to what our simulation produce as of today. So that means we need to still fine tune our simulation a little more, which is what will go on from now on. And also these are few other observations. I just wanted to show you without going into technicalities. What is plotted here is that spectral shape versus the brightness. How bright the galaxies are, it seems that their spectrum depends on the brightness, and the points which are shown with the open thing are basically observational points, and the curves are from our simulation, and you can see that most of our simulations actually go through these points. So this is very interesting observation. And just to show again, in the right hand side, we compare our simulation result with various other simulations which are becoming available in last couple of months, and looks like we are all fine tuning towards the correct parameter space in the point. Okay, this is the same thing which line ratios are also being reproduced. So the point of showing all these things, even though I don't go into the details of technicalities, is that we know how to fine tune a star formation, how to fine tune what kind of emission lines you have to have, and also to see what kind of scattering you need to produce in these regions. Okay, so just to show that we are also able to now do what is known as cosmic reionization. Cosmic reionization means like you start off a universe which was completely neutral, because the radiation decoupled from the matter, and slowly evolving, all the matter is completely neutral because it is no more interacting with radiation, till you form first set of galaxies. So once you form galaxies, the galaxy light can go and start influencing the gas in the surrounding region and start ionizing them. And this goes by the name reionization, because universe started from ionized phase, then it become neutral. Later on, the newly formed galaxies start reionizing them, and that is the phase one has to model. And this also again put constraints on what kind of galaxies you have. Now we have developed a tool to do this also. Okay, so now we are able to get into this physics as well. Just to summarize, what am I doing here? So first I summarized all the observational properties of galaxies. Second thing we say is that we are trying to attempt what kind of simulations you can generate here, where we can start addressing this question by saying that why certain things are like this, what is the what cold dark matter is correct, or our prescription of forming galaxies is correct, our prescription of forming various feedback processes is correct. So we have now a tool for the first time in the country to allow us to explore this possibility without depending mainly on the runs which are performed by somewhere in the world. Just to say, like, are we completely comfortable with all these models? See, this effort has started, it's extremely recent. You can see that's why we have not yet published the first set of papers. This work is just 1 year old. Simulations are still running. So there are some issues. So I will highlight what are the issues we are facing. While we are getting the number density of galaxies up to some level correct, we are not getting the black hole number correctly. So actually our simulations are producing black holes which are at least factor 10 smaller in number per unit volume compared to what has been observed. Again, there are two possibilities. One is that when we are doing numerical simulations, we should worry about whether we have reached a resolution which is correct to do the physics of your interest. For example, if you want to grow black hole, we should allow matter to fall into the black hole through accretion disk and other things. Our simulations do not have spatial and mass resolution to capture this physics very accurately. We do approximate methods of doing accretion, which needs to be fine-tuned. So we have found some other way of addressing this issue. So this has to be addressed. There is a problem in bringing black hole. The second thing is that we have to now, we are producing chemical evolution, but we have not yet got our code written to calculate various observations performed by ALMA. ALMA is a millimeter telescope, which is creating interesting maps of the sky where the same galaxies are seen in carbon and oxygen lines and carbon monoxide. So this implementation we are going to do soon. Basically, we want to include some chemical prescription so that we can do molecules and other things. The reionization models I already showed you. We have some first steps already done, but this has to be now we are in a position to implement this also. So then we want to also do the radiative transport, which we are not doing. See, this photon transport, we are doing it in towards us, but there are certain photons which can get trapped in the galaxy itself, and it's an interesting problem to solve. So now we build a big group across different institutes, basically IITs, TIFR Mumbai, to identify various partners who can build these modules so that we will have a fully complete simulation suite. So that this was lacking in the country for some time. So we now have the tool where we produce the galaxies and large scale structure in a self-consistent way using the simulations with the large HPCs. With this, I conclude. I hope that I just conveyed the basic excitement I have related to this. Okay. Thank you.
So, Professor Santosh, hello, are you able to hear me? Santosh? I think he's not. So, meanwhile, I request Sachindra Naik to moderate the question answer session.
Okay, thank you, Lucas.
Yeah.
So, thank you very much, Professor Srianand, on this exciting talk on this uniform galaxies using recent results and also simulations conducted at IUCA or ongoing at IUCA. It's a really fascinating and it's a very informative talk on this. So now to ask questions in the WebEx, participants please raise your hands and unmute, and then you can ask your questions. Vijay, I saw Vijay, so
yeah, you can raise your hands.
Santosh says
Yes.
he is unable to unmute. Okay.
So I have raised my hand.
Okay.
Can I ask
Yeah,
few
yeah.
questions?
Yes, Vijay.
Yeah. So nice to see you. I have a couple of questions. You mentioned about this hydrogen line that shift that is for different red shifts like going from 13.2 to some 13.4 or something like that, and you attributed that to the size of the universe, right? What about the time scale? So, you said that if it is like 2 times, then you will see the Z value is 3 or something like that. But if I want to, find out the time scale, what when it was, photon was released. So how can I do that? How that I can?
That is where it depends on the cosmology you are assuming. If you
Uh-huh.
take the lambda CDM cosmology, the map I showed, the red color curve I showed, that makes the mapping between redshift and time. So that is the game you will play. For example, with the present cosmology, redshift 13 is 300 million years. If you say that 300 million year is too short, then you can make it 1 billion year by changing the cosmology. You can just say that you don't live in a cosmology which is expanding. You can change the expansion rate, so that this is what is the challenge. So if purely based on physics, if you are finding that it is difficult to form galaxy or stars within 300 million year, you will now say that I will change the cosmology so that I will get more time to form. So that is the idea behind crisis in cosmology. That's why people are interested in this problem.
Why I asked this question is some time ago you were looking for this variation of fine structure constants, right?
Yeah.
So for that, the typical time scale should be something like billion years or something like that. So these spectroscopies are not useful for then, those kind
No,
of
no, you have to think other way around. The
Okay.
age, spectroscopy will be useful only because the age is, since the age is 300 million year, but the light has taken a billion year to come from there to us. Okay, so
I
these are
see.
very good. Actually, they have to spend the maximum time. So if you find, for example, this oxygen 3 doublets in these objects, and if you find the separation between them, they will produce a much better constraint compared to what you get in Redshift 2 or something. So that is one way of looking at it.
Yeah. In fact, some time ago, I had asked you this question that why we can't see highly charged ions in those systems and heavier highly charged ions. So now also you mentioned about these lines from carbon 2 or oxygen 3 and magnesium 2 or something like that. So what prohibits it to see other lines like let us say magnesium 4 plus lines or something like
No,
that?
we have to go to X-ray. That's all. Nothing much more.
I see. So it is
This
the
wavelength
limitation
range,
of the instrument
yeah.
instrument that you have.
Yeah.
I see. I see. And you were mentioning about this. Sorry, I'm asking a couple of questions. If there is not enough time, then I'll stop here. So you're talking about this, simulations, but you didn't mention like it must be involved. That simulation must be involving a lot of hydrodynamics, plasma
Yeah.
physics, and all that.
That-
How do you integrate all of them? So that point was not clear. And also,
No,
how do you take care of the boundary conditions and all those points?
yeah. Okay, that's a good point. I mentioned about. So we have basically taken a code called Gadget, which is publicly available. Okay, but we have incorporated various new things. For example, when there is a prescription for forming stars. Once you form a star, you should worry about what kind of yields which will have, because you have to assume kind of chemical evolution happening, and so there is a way. There are different modules we can add to this code so that we can incorporate this. So we have incorporated yields of this thing, different mass stars, yields of supernovae, AGB stars. So that's why it is taking a lot of time. See, this is like 2.5 years. Till now, we have not published any paper. The idea is to get all these things right, but now I am confident that we are able to. But this fact that we have established this now, that means now we can grow and start including new physics, which was not possible before, right? So that's the. So I can tell you at some other time, if you come to Ayuka or if you meet somewhere else, I can give full details of whatever is physics involved in this.
Okay,
Yeah,
so
my last question is that you talked about this HPC. Where is the challenge in your like HPC simulation? So do you solve some nonlinear equation? That's why you need bigger HPC, or just the dimension?
It is nonlinear equations.
Okay.
Also dynamic range. See,
I see.
we are simulating 150 megaparsec cube box, and we worry about a star which is like in 100 parsec scale. So these scales have to be matched. This cannot be done analytically. See, I spent 10 years doing analytical models.
Analytically, I understand, but if it's
but
not
they are
you are not dealing with the nonlinear equations, then you may not require much memory. Only the number of cores will be useful. Yeah.
here
Okay.
things
Thank
become
you. Thank
highly
you.
nonlinear. Yeah.
Okay.
okay, so now I invite Viresh Singh to unmute yourself and ask question.
Yeah, am I audible?
Yeah. Yes.
Okay. So I have a couple of questions. First question is related to luminosity function. So you said that at redshift z equal to 10, the basically models are under predicting. So
Up to 10, it is fine.
yeah,
Models
beyond
are
10.
yeah.
So is
Around.
it possible if I because you are deriving your luminosity function, observed luminosity function from deep fields, and these have, I believe that they have a smaller area coverage, sky area coverage. So is it possible that they are affected by cosmic variance and somehow they are erroneous and
Yes.
will lead to inconsistency?
That is true. That's why I didn't spend time on the slide. Actually, these numbers are coming down. See, in the beginning, people reported a large number of galaxies with increasing number of observations. This mean is coming down. So it's still possible that for some reason you have observed a statistically higher density region by chance. It's quite possible.
Yes.
But in our case, what is happening is that we are running into even our time step in our simulations. You have to be careful. Because when you go to higher and higher redshift, you want to make sure that we calculate quantities at a time step which is shorter compared to the universe which you are probing. So I am not thinking at present this is a problem, because we have done a small mock run with different resolutions. Then we found that our number of galaxies we produce is proportional to resolution. That means the physics is not converged. So this is what we are addressing now from our side. And you are right, from observational side, cosmic variance is a big problem.
Okay. And the second question I have about the sizes. You said that they are of small sizes of 1 kiloparsec or so, although they are pretty massive, 10 to the power 10 solar mass or so. So is it possible that they are merger-driven systems, and then somehow we are detecting, dense and intense regions and not unable to detect the diffuse,
No. See, the
emission?
density being higher, you can understand, because universe density goes up as 1
No,
plus
I'm not
ZQ.
talking about overall density. I'm sorry, I'm
That's
sorry to
what. That's what.
interrupt you.
Just to take it
For a
that way.
given galaxy, let's say, is it
That's what.
possible that
I'm just explaining
we are
to you.
underestimating the size?
Now I'm just explaining to you. The background density goes as 1 plus Z cube. Okay. And what you call as a galaxy is a region which has 200 times over density compared to the background. See, if you are not dense enough, you will not become a galaxy at that redshift. Otherwise, you will be like an intergalactic space. So by construct regions, only regions which are extremely dense will become galaxies, right? So that part is okay. But this merger itself is a strange quantity. Everything is merger, right? Because the gas is falling into some dark matter potential. So what we are seeing in our simulation, which we have to understand, is that star formation doesn't happen like all gas settle into a disk and then star formation. Actually, stars are formed during the collapse itself because the densities are large. So mostly there is no specific shape to them, but in light you see them some size. But if you, this has been seen in gravitational lens galaxies also. Most of the galaxies are clumpy with most of the lights in clumps. So it is another problem which we are able to see in our simulation. Yeah.
Okay, thank you very much.
Okay, Santosh, is it
Yeah.
possible for you to ask?
Thank you, Professor Srianand. Am I audible now?
Yeah.
Yes.
Yeah. So sorry, earlier somehow I was not able to unmute. So thank you very much for taking us through a very fascinating observations with JWST. I have a couple of quick questions, one on your simulation and another one is on observations. So I'll start with the simulations first. You mentioned you are also simulating the spectrum and various elements. So I just wanted to know, how you are generating the elements? I mean, is the nucleosynthesis also included consistently, or is it like you put it in some fraction or something? How the elements are included in the simulations?
No, elements are created, as I told you. When you have a star, a stellar evolution is tracked in a simple way. And every time a small fraction of the star explodes as a supernova, we track the elements which is created there. So
So the nucleosynthesis is included as a part of the
code,
simulation.
Yeah.
Okay.
So then, for generating spectrum, we generate H2 regions, and whatever metallicity of the gas is being used. So we can even produce non-solar abundances. So it has been tracked. Yeah.
Thanks. And the other question was about these LRDs, little red dots, which I assume can be considered as the equivalent of modern day AGNs of very young universe. So observationally, their fraction, is it consistent with the present day AGN fraction, or is it a difference? I mean, what do we know?
I think the most interesting constraint is not present day. You take redshift 6, people have found large number of supermassive black holes.
Yeah.
Suppose if you take these guys as the progenitors for the supermassive black holes, suppose you say that these LRDs at redshift 10 become supermassive black holes at redshift of 6 or something. These numbers are not matching. LRDs are 10 times
not
more.
matching. Okay.
So somehow we have to make them disappear.
Yeah.
They are active at that time. They are not so active at redshift 6. See, there is still a lot of, I think it's very exploratory stage. And another, Santosh, what you will be interested in is that other thing is that they are not X-ray. X-ray detection is not there.
Oh, okay.
People have looked at X-ray from deep fields. They are not detecting. Similarly, they looked at radio emission in deep field. They are not detecting. So the optical to radio is less, optical to X-ray is less.
No, Chandra sensitivity, is it sufficient to probe this, or you require a more sensitive observations for X-ray? Because I
See,
don't
they are
think
using
apart from Chandra, anything else can be used here.
no, but these guys are well separated, so you can use, right?
Okay.
Erosita they are using, I think.
Okay, Erosita, but I think that in terms of deep sensitivity, it will be limited, significantly limited compared to
ESF
Chandra.
may be
But that's a
smaller.
good problem. I mean, it
Yeah.
can be considered as a
Yeah.
Okay, so Namit, you have raised your hand.
Hi, Srianand.
Namit?
Can you hear me?
Yes.
Yes.
Hi. Thanks for a very interesting talk. So I have a question related to the black hole formation. Part of it you kind of commented towards the end. So I was just wondering that when you showed the timeline, the flowchart kind of a thing, is it clear at what point in that flowchart do you start getting the black hole? And of course, you said that it's not growing big enough. These black holes are not growing big enough. So the other related question was that what is so dramatic about z equal to 10, that the moment you go beyond z equal to 10, suddenly the whole thing just meaning you're finding less number. But
Now,
below z,
let me just address the second one. Beyond 10, there are two observational issues. There are two issues. One is related to observation, which was mentioned in the previous conversation, because these galaxies are detected in a small area, so we have to wait till we get something done. The second thing is numerically, since we are around 300 million year, our numerical time step is closer to this age itself. So a lot of physics is not converging, even in numerical calculations. I think this is where the efforts are being made to address it. So before calling that, see, since you cannot say that my cosmology has changed between 300 million years to 400 million years. So most of the belief now is that more or less physics is correct, but the parameters can evolve. So for example, we ourselves have found that if you make efficiency of setting up wind, blowing away the gas from the galaxy, if you make it as less efficient by a factor √2, we are able to get these galaxies. I didn't present it here because still we are investigating that, and we are able to get factor 2 excess by just playing with the local physics, whether wind can be set up. But this is all allowed by, if you just put cooling efficiency is high and all, this can be done. Coming back to black hole, there are two kinds of black holes which are interesting for us. One is that supermassive black hole. Another is that stellar mass black hole. A stellar mass black hole is interesting for GW gravitational wave science. So that we will not be able to simulate because our simulation resolution is like 10 to the power 5 solar mass is one particle. So this is where the black hole problem comes. If I start with a black hole which is 100 solar mass, in simulation I cannot keep the black hole anywhere. Because if a 100 solar mass interact with 10 to the power 5 solar mass particle, it will be kicked out. So how to keep a seed black hole into the center and let it go through the region and accrete by some physics is a big challenge. So people are coming with some schemes in the numerical physics wise. The problem is how to make a 10 to the power 5 or 10 to the power 4 solar mass core collapse black hole. People think that why can't you collapse the initial collapse going into the black hole? That means we have to make sure there is no angular momentum. Then you have to make sure that there is no perturbation, which makes while collapsing, the gas should not become clumps. If it becomes clump, right, then you will not collapse into the black hole. So there are too many conditions which are required. So I think this is a growing field now. Like last 1 year, there are a lot of discussions on how to form the seed black hole. From a numerical side, how if I give a black hole, how will you make sure that the black hole is sitting inside the galaxy and accreting? So the physics I am talking about is that I am given a black hole, and the black hole is wandering around all over the place. Wherever it finds gas and star, it is accumulating, and that physics we are trying to fix it. But we are not addressing how to get the first black hole itself. That is a different problem.
Okay, thanks a lot.
Okay, so I don't see any hands raised in the WebEx channel, but I have a small question. This is regarding this potential of dark matter in the galaxy. You said this dark matter is governing the motion of the particles in the galaxy. So understanding or investigating the motion of these particles in the galaxy, can you have or say something about the location of dark matter in the galaxy?
Yes, to some extent, yes, because the dark matter affects not only galaxy, it affects the whole universe expansion, right? So that's where this not only you look at one galaxy, you also look at how galaxies are aligned with respect to each other. This is known as clustering. You also look, if I find a galaxy, what is the probability that I will find another galaxy within a distance r in a random thing? So that is also governed by the gravitational forces. So nature of the dark matter is fixed by the expansion of the universe, how the galaxies, individual galaxies, stars are rotating in a galaxy, as well as how galaxies are coordinating with each other. So this problem of what is the density profile of galaxy is a universal problem, which can be, again, you can address it depending upon what physics you are including. We are treating as a non-interacting particle interact only through gravity. But people are also attempting to make a condition saying that when they are closer than some value, they can have a self-interaction. So this has not been proved. Suppose you say that, then that can change the way a typical galaxy will look like at the smallest, in the central regions, it will have some physics related to that. And such interacting dark matter will also emit some radiation. So there are physics related to that, which will change the way certain things looks like. But we are doing conventional thing only. We are just taking non-interacting dark matter part at this stage.
Okay, so another part is this galaxies, again, this supermassive black hole at the center.
Yes.
And we think that this black hole is holding all the stars or most of the stars in the galaxy. If it is at the center of the galaxy, which is holding the stars and components in the galaxy, then this discrepancy in the number, whatever you estimated from simulation and observation, that means there are some galaxies where supermassive black hole is not at the center.
No, I must just say that there are some models we have run up to redshift 0 just to make sure that we are matching with other people. And we are finding there is no problem with the black holes locally. Black hole number density matches exactly at redshift 0. At redshift 6, we are matching with black hole numbers. There is no problem. Problem is all related to redshift 8, 9, 10. So the take-home message is that when you are dealing with very high redshift, since the time scale is very small, the tendency is to say physics is wrong or physics is correct or whatever. But I am just highlighting that, and observational side, observations have to improve because we are not yet reached that stage where we can trust them. Simulation side, I'm saying that since we are dealing with small number, we have to make sure that our time resolution is completely captured. So if you are saying whether you produce correct black hole at redshift 6, yes, we are producing correct number of black hole at redshift 5 and 6. But our aim is to produce all of them at redshift 7. That means there are some new physics involved, or our physics at a small time scale has to be accurately modeled. So this is the challenge. I think that's the take-home message for this talk.
Okay, so thank you very much. So I don't see any other hands raised in the WebEx channel. So Lucas.
So thank you, Professor Naik, and thank you, sir, for very nicely interacting with our audiences. We are almost coming to the end, and before that, I request my colleague, Dr. Manas Samal, to present vote of thanks.
Am I audible?
Yeah.
Yes.
Yeah, thank you, Professor Sao. Friends, it is an honor to propose vote of thanks for today's Vyakhyaan. First of all, on behalf of Director PRL and the entire PRL community, I would like to express our sincere gratitude to today's speaker, Professor Srianand, for sharing his insights on the early universe formation and evolution. Today's Vyakhyaan was particularly timely, given the fact that ALMA and JWST is providing outstanding results on distance cosmos, and the forthcoming generation optical IR and radio telescope will even go deeper and unveil the much deeper, much earlier universe. So what we also learned that from this his Vyakhyaan is that how observations, simulations, and theoretical frameworks are collectively can advance our understanding of cosmic evolution, and as he demonstrated how the simulations are actually challenging the observations, vice versa. So we need to learn that. I'm sure that like me and many of our colleagues and participants are greatly benefited from his talk. Professor Anand, once again, we thank you for your valuable time and delivering such a enlightening lecture. Thank you. Next, on behalf of Vyakhyaan Committee, I would like to thank Professor Anil Bharadwaj, Director PRL, Professor Pallam Raju, Dean PRL, for their constant guidance and continued efforts in ensuring that these lectures keep going without any hindrance. I also thank Professor Badawale, Professor Nayak, and the CNIT team for their valuable help in conducting this Vyakhyaan. Finally, our special thanks to all our participants and viewers who have joined us through WebEx panel or YouTube platforms. Thank you all for your time. With this, we come to the very end of today's chapter of Pyarel Ka Amrut Vyakhyaan. Before I sign, I want to emphasize that today we have another very special Vyakhyaan at 4:15 p.m. Please do join and invite your colleagues to join us this special Vyakhyaan at KR Raghunathan Auditorium at 4 p.m. on the very special topic Dhyan Anand or Srishta Ka Antrik Jagran. It will be live guided by, and it will be kind of live guided meditation workshop, and will be delivered by Padma Bhushan Sri Kamlesh Patelji. Please do join again at 4:15 p.m. Have a great day. Thank you. Thank you, Professor Anand and everybody.
Thank you.
Thank you, Srianand.